just want to introduce our speaker, Bruce Skinner. He joined Caloris in 2008 as sales manager. He holds a bachelor's degree in chemical engineering from the University of Delaware and has 35 years of professional experience in the chemical, food, and dairy industries. Throughout his professional career, Bruce has focused on creating and successfully implementing process concepts and solutions that meet the specific requirements and needs of each customer's unique product applications. With that, I'm going to turn over the session to Bruce.
Thank you, Missy, and good afternoon, everyone. Thank you for giving us a little bit of your time this afternoon. And I would put the video on just for a moment so you could put a face to the disembodied voice, and in a second I'll turn that back off so I can put the focus on my PowerPoint slides. And again, thank you for joining us today. The topic, as we put these programs together, looking for an opportunity to stay in touch with our customer base in this unique time of physical distancing, we thought we would start with these webinar sessions. And the first one we thought we would start with was about as basic as you can get in evaporators, and that is the vacuum and venting issue. And in the world of evaporators, when I started 28 years ago, there were two key points that were emphasized to me, and they are that 90% of all evaporator performance problems are due to vacuum leaks. And the second one is there is no such thing as a small vacuum leak. And not all evaporators operate under vacuum. However, in our industries that I believe most of you, from what I saw the registrations, are in the food and dairy industry, we do operate under vacuum, and for various specific reasons. And vacuum gives us a lot of flexibility in the performance of removing water, but it also introduces some challenges. So as we move, before I get too far into my presentation, I wanted to highlight a couple of key points of vocabulary concepts that we'll be discussing during my talk here. The first one is vacuum. What do we mean by vacuum? And that is, from the chart you can see here, atmospheric pressure, 14.7 psia absolute, also 0 inches mercury vacuum. That's the atmospheric pressure at sea level that we're all living in. As you start to pull vacuum, and most commonly in our industries, we refer to inches of mercury of vacuum. And typically in a lot of our operator applications, we're running down around 20 to 27 inches of mercury, vacuum. And you can see the relatively low absolute pressure. The second concept we'll talk about here is, and why do we operate under vacuum? And that is because we can boil water at a lower temperature. And I mean, most of us are familiar with the phenomenon. If you try and boil water on top of a mountain and try and cook something in that boiling water, it takes longer. Why? Because slightly lower pressure at altitude, and the temperature of that water is boiling at a lower temperature. And we take advantage of that in our industry by running at fairly substantial vacuums, 25 inches of mercury vacuum. Water boils at 133 degrees Fahrenheit. And a variety of reasons why we do that, but primarily in evaporators, we're trying to concentrate a solid rather than cook it. And the example I like to use is eggs, whole eggs. We can concentrate whole eggs in an evaporator under vacuum. However, if you get that temperature up to about 120 degrees Fahrenheit, you're no longer just concentrating, you're cooking those eggs, and after a little while, you're going to get the hydroblaster out to get those scrambled eggs out of your evaporator. Now, also a phenomenon that happens when you pull vacuum in order to boil at a lower temperature, the specific volume of your steam, your saturated water vapor, significantly increases. And you can see here the specific volume at atmospheric pressure of a pound of steam is 26.8 cubic feet. You pull vacuum and that same pound of steam now occupies 146 cubic feet, or over 5 times as much volume. Air also expands under vacuum, and a pound of air at 25 inches of vacuum will similarly occupy more than 5 times as much space as it did at atmospheric pressure. And I also make the point here that air is a denser gas than steam. And you'll hear me using the term throughout my talk here of non-condensable gases and air, and I will tend to use those interchangeably. Non-condensable gases are principally oxygen and nitrogen, the principal components of air. And that is steam is a gas, which can condense. Air does not in our normal operating conditions. The third term that I just want to review here is the difference between sensible heat and latent heat. And sensible heat is the energy, the heat it takes to increase the temperature of something such as a liquid. And the units here are kilograms. A kilogram of water requires 1 kilocalorie of energy to raise it 1 degree C. And to raise the temperature of water from 0 degrees, near freezing, up to 100 degrees C, atmospheric boiling, 100 kilocalories of energy to increase the temperature of that 1 kilogram of water. Now, and air has a heat capacity of only 0.24, 1/4 of the heat capacity of water. Latent heat is the energy that's released when you condense steam or a condensable vapor to a liquid form. And there's much more energy involved in that step. And for example, and the example I have here is 1 kilogram of water now at 100 degrees Celsius. The energy required to convert that kilogram of water from liquid to vapor form is 539 kilocalories, or over 5 times as much energy to convert it from liquid to vapor phase. Similarly, when you condense a kilogram of water vapor, steam, you liberate that energy, gives it off. So with those key points in mind, I'll get into the general concepts here of evaporation. And what I'm showing here is a falling film evaporator, which I believe most of you are going to be familiar with, although the concepts work for any shell and tube or evaporator heater, even at atmospheric pressure. In an evaporator like this, the product comes in the top, flows down tubes, a heating source, steam, water vapor enters the shell, you heat the product, flows out the bottom as a concentrated product with water vapor released from your product, going through the vapor separator and out as vapor. And if this were a forced circulation evaporator, where those tubes would be flooded instead of the falling film design here. Getting into the falling film design, ideally the yellow liquid coming in the top is at product boiling temperature as it enters. And it's distributed so it flows down the inside of a tube. You have steam introduced into the outside of the tube, and that steam condenses, liberating that 539 kilocalories of energy for each kilogram of steam that enters in, transferring that energy into the liquid on the inside. It's already at boiling temperature, so that energy is used to release or evaporate water content from the product as it's flowing down the inside of the tube. Very effective way of transferring energy to the product in order to liberate the water content. And I thought it would be interesting here to show the inside of a tube and shell heat exchanger here, and whether it's in a vertical orientation as a falling film heat exchanger or a horizontal as a forced circulation. You can see this is a partially filled shell and tube heat exchanger. And when all of those open holes are filled with tubes, you can see it becomes a forest of tubes with not a lot of space in between, but it's certainly enough space for steam, water vapor to get around and inside and contact all of those tubes. And we do this so that we can pack as much surface area as possible into a vessel. And those baffles that you see serve several purposes, primarily to help keep those tubes spaced properly and keep them from moving around so they don't bang around and break. But also it helps to distribute the vapor flow. As steam comes in, it promotes the horizontal flow of that steam through the tube bundles rather than just straight down the length of the heat exchanger. Now, it's the topic here is vacuum and venting, and generally in both of those circumstances, what we're trying to do is get air out of the system, but we're also fighting to keep air out of the system. And no evaporator is 100% perfectly tight. There's always potentials for leaks. We try to build them as tight as we can. What are those common sources of air leaking in? Manway gaskets. Those are and the top heads of the calandrias and the heat exchangers. Those are heads, and manways are opened fairly regularly for inspection purposes. And it's you have to take care to make sure that those gaskets are maintained in good order and that they're not crimped or knocked out of place when you're closing up your head or your manway. Tri-clamp fittings, and in particular on evaporators as they age over time, anyone who's worked with one knows that it becomes more of a challenge to get those pipes and tubes to line up so that you can get that tri-clamp fitting to fit properly. And if it's ever so slightly off, it becomes a source of an air leak, even if it's going to be a flooded pipe. Say on the discharge of a pump, as long as it's under vacuum on the inside, it can still suck air in through. Pump seals, and on most evaporator applications, and when we've got vacuum, we need to use a double mechanical seal with a water flush to try to keep pressure on that seal so that we don't leak air in through the pump seals. And if there is a malfunctioning seal or poor seal water supply, that can become a source of air leaks. And then the last one is in the feed product itself. Dissolved air, dissolved non-condensable gases, carbon dioxide, it's any number of non-condensable gases can be introduced into your system with the feed. And that's an inevitable aspect of evaporators that we need to take into account and design features to remove that non-condensable gas that's coming into the system. What happens when we get non-condensable gases into the system? Air. So it mixes with, on the shell side, mixes with the steam, but it doesn't condense. And a film of that non-condensable gas starts to form and can collect at the outside surface of the tube, and it becomes an insulating barrier, referring back to the fact that air has a heat capacity 1/4 of water. It's not a very good heat transfer medium. And while you've got steam trying to get to the surface of your tube to condense and release energy inside, as you get air inside the system, if you don't get it out of there, it impedes the heat transfer efficiency of your tubes. So all calandrias and preheaters, anything that is a vapor heating on the shell of your device, you need to remove continuously non-condensable gases. So all evaporator systems, whether you're at atmospheric pressure or operating under vacuum, they all have to, energy in minus energy out is zero. Whatever energy goes into the system has to come out of the system. And in an ideally operating and designed evaporator, we have no radiant heat loss from the system. The vent is pulling only non-condensable gases out, no excess waste heat steam. So we're putting energy in with steam and electrical power. We're bringing product in. We have product coming out and condensate coming out and non-condensable gases being pulled out of the system. And if the energy balance is perfect, we don't have any rejection of waste heat. Now, of course, a real evaporator, we're always going to have a little bit of radiant heat loss from the equipment. And with that venting, we are pulling some steam, vapor out along with the non-condensable gases. It's really the only way to make sure we're getting those non-condensable gases out is to sacrifice some of our energy, some of our steam vapor. And that ends up going into the waste heat collection systems, typically a surface condenser, barometric condenser, and that is removed from the system as the cooling medium. And it's common on on evaporator systems that they'll run a 20 Fahrenheit heat rejection of, say, cooling tower water circulating through the system. And why do we sacrifice a little bit of that energy? Because the energy loss is a trade-off we're willing to take in order to get the non-condensable gases out of the system. Because if we don't, over time, those non-condensable gases are going to restrict our available heat transfer surface area and reduce the efficiency of our evaporator. And non-condensable gases will have a tendency to collect at the ends of a tube and shell heat exchanger, regardless of what orientation it is in. In a vertical orientation, like shown here in a falling film evaporator, tendency more for those non-condensable gases to collect towards the bottom because of the density of air being higher than the density of steam. And in order to get those non-condensable gases out, we need to have vent both the top and bottom of our calandria. We also have condensate that needs to come out of the system, bringing steam in. We need to take the liquid condensate out of the shell. We need to pull our non-condensable gases out. And those air-laden non-condensable gas vent streams are usually taken straight to a waste heat removal condenser system and then pulled from the system by most commonly liquid ring vacuum pumps, steam jets, various techniques in order to pull vacuum. And again, here I'm showing the inside of this tube and shell heat exchanger. And typically we're bringing our steam, our saturated water vapors into the middle, and those vapors need to flow horizontally plus up and down the length of this shell and tube heat exchanger so that we can distribute those steam vapors across all of those tube surfaces, take advantage of it. And with them, our non-condensable gases are coming along with it. And as you condense the steam water vapor, you know, on a mass basis and taking a volume, the non-condensable gases become more prevalent as it distributes towards the ends. And that's why the non-condensable gases will have a tendency to collect towards the ends of that heat exchanger. Cooling water loops, that's where the waste heat is generally taken. And it's most commonly, we are designing with surface condensers so that we have non-contact with our cooling water. Waste vapor goes into the shell of a shell and tube heat exchanger. Again, we need to pull venting because we've got non-condensable gases that we're dumping into this shell of this surface condenser, and we need to pull them out and pull out our condensate. So various methods that are used in our evaporator designs for vacuum control are air bleed control valves on the shell of the condenser. And this may seem somewhat counterintuitive, but it is a very effective way to control the temperature. And the surface condenser is the tail end of the evaporator, the lowest temperature point. And if you want to raise your boiling temperature in your evaporator, the fastest way to do it is to reduce the vacuum level in the surface condenser And an extremely effective way to do that is to open up a small air bleed valve and a little bit of air going in there, because the specific volume increases so quickly, will very quickly displace condensing vapors from the surface areas of those condenser tubes, and your pressure is going to increase. Alternative ways are throttling the cooling water flow. If you reduce the flow, you get less cooling through the tubes, and you will, in effect, raise the vacuum level inside the shell of that condenser. Or, and a waste vapor coming into the shell, you can put a throttling valve on that and take a pressure drop across that valve and let the condenser be at a deeper vacuum level than your last effect of the evaporator system. And for MVR evaporators, which run very close to a neutral energy balance, you can also control vacuums by simply injecting a little bit of steam into the system, which puts more load on the waste removal surface condenser, and you effectively get an increase in or a decrease in the vacuum, pressure increases in the system, and you start to see, and you'll boil at a higher temperature. And it's not just the calandrias, our main heat exchangers, but all shell and tube heat exchangers of the evaporator system, including the preheaters, as we're showing here, need to be vented both top and bottom. You can't have any dead ends, otherwise you start losing effective surface area. And if you don't have effective preheating of your product before it gets into the evaporator, the main calandria, your calandria is no longer functioning as an evaporator, but it starts to be a preheater at the top, and you're again losing effective surface area. You're not taking advantage of the proper design. And another key point here, you'll see at the bottom, and also shown in the picture, you see the pink lines with an orifice. Those, showing the vent line being pulled out of the bottom of these shell and tube heat exchangers. And below that, the solid line is the condensate coming out. And we need to design the condensate removal of any shell and tube heat exchanger so that the condensed water vapors are pulled out and do not fill and start to block that vacuum outlet. Otherwise, we cannot vent the non-condensable gases out of the system if we start to block those. And what I'm showing here is with the orifice, that's the most common way that when we commission an evaporator is we select the proper size orifice hole in order to allow a certain portion of the steam as well as non-condensable gases to routinely vent out of the heat exchanger all the time. It can be done with a valve. However, a valve can be adjusted. And what we find is that when we put an orifice in there and we fix it, it stays and is consistently reproducible on its performance for years to come. Quickly highlighting here again the concept of the specific volume of steam, or in this particular case, steam increasing as temperature decreases. You can see, from 180 down to 150, not much of a specific volume increase, but then it starts to increase fairly quickly. And how that can affect us in evaporators is in multiple ways. In a multiple effect evaporator, a 3-effect evaporator being shown here, we're bringing a steam source into our first effect, evaporating some water vapor from our product, which becomes the heating vapors in our second effect. That second effect operates at a lower temperature, lower absolute pressure, evaporates more product, or more water from the product, becomes the heating source in the third effect, again operating at a deeper vacuum, and we get some more evaporation, and those vapors are then sent to a surface condenser to extract that waste heat. And in round numbers, for a pound of steam coming in, you can evaporate 3 pounds of water in a 3-effect evaporator, and you have the equivalent heat rejection into the cooling tower as that steam coming in. It's a, energy in equals energy out. Now, what's happening here is each time we go to a deeper vacuum, specific volumes increase. So the space occupied by a pound of water vapor evaporated in effect 1 is much less than the volume of that same 1 pound of vapor evaporating off of effect 3. And likewise, if we've got non-condensable gases in there, they are also occupying greater amounts of space. For example, if we have non-condensable gases that come into the first effect with our product feed and are released from the product along with evaporating water, now those vapors, or those non-condensable gases, will go through the first effect vapor separator into the shell of the second effect. Now that second effect, we've got those non-condensable gases in there which have expanded because of the lower absolute pressure level, and we're losing effective surface area in effect 2, which means effect 2 is not going to evaporate as much as effect 1 did. And therefore, we are getting less evaporation out of effect 3 because we've got less vapors coming over to that. So it's non-condensable gases in the feed, if we come into effect 1, bites us twice in reduced performance in effects 2 and 3. If we know we have a feed with non-condensable gases that we have to degas, a common technique is to bring that feed in to effect 3. Allow that feed to degas and let those non-condensable gases exit through the third effect vapor separator straight to the surface condenser. And that's a common technique in multiple effect evaporators. If we are on a single effect evaporator, where, and particularly MVR evaporators, where what we evaporate is being compressed and creating the steam that goes into the shell of our evaporator, then we usually need to add a separate degassing step for the feed before the feed gets into the evaporator. Because otherwise, that non-condensable gas really begins to bite quickly and cause problems. So the biggest symptom of vacuum and venting issues is the evaporator's running hot. And why is that? Well, if I'm getting a vacuum leak into my system, those non-condensable gases are choking up my system and they're ending up in the surface condenser. And unless my surface condenser is oversized and able to handle excessive amounts of non-condensable gas, I'm going to build pressure in that shell of that condenser, and the pressure in my third effect is going to start increasing. And the only way to maintain that evaporation is to increase the heating temperature on that first effect. And that's when an evaporator starts running hot, when that last effect and the surface condenser start running hotter than they have been, inevitably, always the first place to start looking is vacuum leaks. And also in alternately insufficient venting. If something has happened to my venting, is my condensate building up in the shell of one of my calandrias? And that's why we almost always put a sight glass on the side of the shell of all of our heat exchangers so that you can see the condensate level relative to the condensate outlet. And if you can't see that condensate level, that's usually an indication that that condensate level has risen. It might be blocking your vent, or your vent outlet. Excessive fouling is also a symptom of running hot. It's not always vacuum and venting issues. And that's, if you've got fouling of your inside of your tubes, of course, that is a resistance to heat transfer. And the only way to overcome that is by putting more heat into the system. And that can be from poor liquid distribution, inadequate CIPing, it's the wetting rates of the evaporator have changed. It can also be the cooling tower, and that's always something to check, is what is the heat rejection performance of your cooling water. It's what is the temperature delta T you're seeing. As the inlet and outlet temperatures changing from what they were? It can be, you know, if the fill in your tower is collapsed and you're not cooling that water off before it returns again, you're losing that cooling capacity. And scale, similar to product fouling on the inside of your calandria tubes. You know, mineral fouling on the inside of those surface condenser tubes will also rob you of heat transfer performance. And then the vacuum pump. And it's always important to make sure that your vacuum pump has got good service water so that it's performing effectively and able to remove the non-condensable gases out of the system, specifically from the surface condenser. Because if the vacuum pump is sucking and it's not pulling the non-condensable gases out, it's backing up all through the system. So how do we detect vacuum leaks? And it's, you know, I put the first note here, old school, you know, cigar smoke. If you have a suspected area where you think there's an air leak, and you were to have the luxury of, you know, sucking on a cigar and then blowing the smoke towards that leak, you'll be able to see it sucking in. Of course, for most of us in our food applications, that's just not a possibility. So in current operating plants, the first thing we like to do, and we always do on a new evaporator system, is we pull vacuum and we shut the system off. And it should be designed with check valves and everything you need to hold vacuum. And pull vacuum, shut it down, and go away for the night. And come back the next day and see what your vacuum level is. And we will usually allow a leak rate of about ½ an inch of mercury per hour. So if you go away for 10 hours, you come back and you've lost 5 inches. If you started, when you went away at 25 inches and you come back and you're at 20 inches, now that's over 10 hours, that's really not bad. But if you come back and you've lost, you know, you're down to 10 inches and you've lost 15, that's a good indication that you've got a leak somewhere. And it's always nice to be able to do that when the system is down, because it's usually quieter and you can walk around listening for those leaks. Now, of course, once an evaporator is commissioned and up and running, it's very rare that you have that opportunity to shut it down and listen in silence. So the next step is, you know, you can use soapy water and a squirt bottle and some soapy water, and you will see it starting to foam and the foam being sucked in around a leak if you can find a suspected leak spot, such as on a gasket. For a broader look at an overall evaporator system, very effective are the ultrasonic leak detector devices. And they require some training to use properly, and particularly in a loud TVR evaporator process room where it can be hard to hear much of anything. You need to be very focused in using the device in order to find those leak spots. But it's surprisingly effective. When somebody knows how they're using one, they can go around and routinely look for leaks. And any evaporator system over time is always going to develop leaks. They're metal devices that are heating and occasionally shutting down and cooling, and you've got thermal expansion and contraction. And sooner or later, we're going to find, you know, leak spots developing. Occasionally, we do need to go to the option of water filling, which is why when we're designing a new evaporator system, the catastrophic weight requirement for the foundation is always a water-filled scenario. And that's, you know, we may not necessarily be able to fill it all the way. On an MVR evaporator, we can only really fill as high as the vapor ducting will allow. However, it is an extremely effective tool when it can be used to fill the shell and or the product sides of your heat exchangers and your equipment, and that water will show you where a leak is. And if you're leaking water out, you're certainly sucking air in when you pull vacuum. And as a general rule, if you are walking around a plant and you suspect, you're running hot and you suspect you've got some vacuum leaks, or maybe you're not venting properly, it doesn't hurt to go around and just put your hand on the surface of the shell and tube heat exchangers at the low end, carefully, of course, because you will find that if you've got a heat exchanger where you are backing up air at the end, that air over time, the surface temperature of that heat exchanger will be relatively cool to the touch, rather than the 150 or 170 degree Fahrenheit temperature you're expecting to feel when you put your hand to it. Those are just some of the general techniques that are used for walking around and trying to find vacuum leaks on an operating evaporator system. Vacuum leak monitoring is something we're doing on pretty much all of our evaporators nowadays, is an airflow meter on the vacuum pump discharge. And any evaporator is going to pull, always a little bit of non-condensable gases through the system. So that's going to be your normal baseline on a tight evaporator system. And once you establish you've got a good tight evaporator and you establish what your normal volumetric flow of non-condensable gas discharging from that vacuum pump is, then over time, if you see that value increasing, that is an indication that you're introducing air, non-condensable gases from a source. It might be in your feed, or more likely than not, you've developed a vacuum leak somewhere in the system. And I believe I've run my time here, so I do want to thank you for your time and attention today. I hope this was a few nuggets maybe of just a refresher probably for a lot of you on what's going on inside an evaporator and why proper venting and vacuum control are important to maintain effective performance of your evaporator systems. I have not been monitoring if there have been any comments going along here along the way.
There have been a couple questions, so thank you, Bruce. And if we want to jump right into these questions, and if anybody else has questions, you can use the Q&A button at the bottom of your screen to ask your question. The first question is, what level of automation in a falling film evaporator allows you to optimize operation and troubleshoot predictively?
Okay, well, that's there is no simple answer to that, because it depends on whether it's a single effect steam heated evaporator or a multiple effect steam heated or an MVR evaporator. You can almost say that there's no such thing as too much instrumentation. What is important and critical information is pressures on the calandria shells where you've got vapor phases, temperatures on your product streams coming in and out of your systems, so that you can do an energy balance and you can monitor are you seeing a temperature rise, an inability to maintain your steady state conditions, or are your temperatures increasing throughout the course of a run? And little things like your conductivity monitoring of your condensate streams and the airflow meter on the vacuum pumps are all very nice to have in order to model and predict and see what's going on inside these vessels that you can't really see in. I hope that helped.
Okay. And then the second question is, what type of seal plan is recommended for pumps?
Okay, well, that's any pump that is either pulling from or delivering to a vacuum condition. We always use double mechanical seal. And that's with a water seal in between those two to maintain enough pressure so that you're not sucking air through the seal and into your system.
Okay. Well, those are all the questions that we have. I want to thank everybody again for attending and let you know that this is part of a new series that we are offering of, at least for the time being, weekly webinars. So the next one will be this time next Thursday, 3 o'clock Gary Maxon, our membrane systems manager, will be offering a webinar on boiler water RO. Same format, brief presentation followed by Q&A, and you can register for that right now on our website. The recording for this and the links to register for all of our upcoming webinars is caloris.com/caloris-webinars. Everybody will be receiving an email after this presentation with that information. But if you want to stay in regular contact with us, I do encourage you to join our mailing list, and you can do that from any page on our website. Just scroll all the way to the bottom and enter your email where it says join our mailing list. We only send a weekly email. It's our new e-newsletter, which contains industry headlines and announcements for programming such as this. So we do hope that you'll join us there. If you have any questions that you didn't want to, oh, I have actually one more question for you, Bruce. For an MVR application, would venting before the MVR fan be an option for removing the air instead of a degassing step before the evaporator?
And the simple answer to that is no. On the suction of the MVR fan, we want saturated water vapor that we are going to enter into the fan and compress to a higher pressure so that we're creating our steam source. The problem is there's really no effective way to separate the air, the non-condensable gases, from the water vapor on the suction of that, unless you go through a process of condensing all that water vapor so you can then extract the air, and then we've lost the effective value of that steam. So the answer is no.
Okay.
Not that I'm aware of.
All right. If you have any additional questions, you can feel free to send email to info@caloris.com. That comes directly to me, and I'll get back to you, or send your question on to our engineering team for somebody to get back to you right away. And we are also accepting suggestions for topics you'd like to see as part of this webinar series. In addition to the RO webinar we're offering next week, we have a spray dryer troubleshooting webinar coming up on May 7th, and an MVR evaporator upgrades webinar on May 14th. So we do hope to see you for one or more of these upcoming webinars.